was not there for the last session, so I am recording it again. So what we have discussed in the last session. So the first question we have discussed is on the metal plate, uh, one ion monovalent group per 2 nanometer whole square is present. The surface is immersed in an aqueous solution containing A molar KCl. Calculate the inverse Debye length in nanometer. Calculate the surface potential Phi naught, psi naught in volt for two different values of A. The epsilon r of the solution is given as 78.4. A for the first case is 0.1 and another is 0.01, and we have find out answer to be 0.96 nanometer and 3.04 nanometer. So here is the solution to this question. So basically it is a set of 4 questions for two cases A and B. So Kb, E, the temperature is taken to be 298 Kelvin. These are constant. E is 1.6 into 10 - 19 coulomb. So kappa inverse we find out using this formula 2B's. So it's actually 0.96 nanometer. So after solving this we get it, and we have also verified this using the formula that is given in the lecture, that is this constant you can calculate for the when epsilon is 78.5 around. So you can calculate this constant, and the only on which the kappa depends is the Z and the M molarity of the solution. So we from here we found out it to be 0.96 nanometer, and we verified that the formula and this formula are giving the same answer. So that is the solution for the case A. For the case B, we have calculated it to be just by putting M here. Z is same, so it is KCl. So KCl is a Z. So for the case of KCl, Z plus Z minus ratio should be 1:1. It's a symmetric solution, so Z should be 1, and so M here is 0.01 for the second case. So when we substitute it here in this formula, we get B to be 3.04 nanometer. And in order to verify, so there is a doubt, so we have find out the value this, and this is coming out to be this, and this multiplied by this thing is making what this formula. Now the another part is calculate the surface potential psi naught in terms of voltage. So psi naught, as discussed in the lecture, that depends upon the surface charge density sigma star. Kappa inverse is the inverse Debye length that we have just calculated, epsilon naught into epsilon r. So the important part is to calculate sigma star, that is surface charge density. So the surface charge density is given, so it is a monovalent group. So one ion has having a charge of 1.6 into 10 - 19 coulomb, 1 2 nanometer square. So it is 1.6 into 10 - 19 divided by 2 nanometer square. So it is 4 into 10 - 18. So it becomes 0.96. So this is the this complete thing is the surface charge density. This we have calculated already. 0.90 minus 9, and this is 78.4. Epsilon 8.85 is the epsilon naught, and what we get is this. Now again, for the second case, the only thing that changed is this kappa inverse, and this will remain same for the same plate. The solution is changed because the molarity is changed, and so the Debye length is changed, and so we calculate psi naught to be this much volt. So these are the two parts of this solution. Now I hope it is clear. So here we have just calculated the kappa inverse for the two cases, and so the psi naught value. So psi naught is given, that is monovalent group, so one electron, so it is 1.6 into 10 - 19 divided by 4. Okay, I hope it is clear. Now we have another question to discuss that is much more important. So we have to calculate the inverse Debye length for the case when a charged surface is immersed in an aqueous solution containing 0.01 molar of asymmetric electrolyte of type. So we have basically two questions here. So in first case the ratio is like this, 1:2, and in another case the ratio is 3:2. So here, if we consider the temperature to be 25 degrees centigrade and epsilon r of the solution to be 78.5 for the solution, So the ratio is this. So for this case to be valid, the salt should be of this form x to y. So when it dissociates into 2 times of x plus y times y of minus 2. So if 0.01 mole of this we have, then it dissociates into we have 0.02 molar x and 0.01 mole of y. So m1 becomes 0.02, m2 becomes 0.01, and the valency for this is +1 and for this is -2. So the important factor that we have to find is this sigma zi mi square, and so z1 square into m1 plus z2 square into m2. So what we get is 1 into 0.02 plus 4 into 0.01. So it's 4 into 0.01, and what we get is 0.06. And this formula is already there in the lecture, so this prefactor is already calculated, and you can also see this in the textbook that is we usually follow, that is Rajgopalan. So here this factor is 4.3 into 10 minus 10 sigma zi square mi to the power -1 by 2. So when we substitute is, what we get is the kappa inverse to be 1.76 nanometer. Now for the case of second, so z plus and so the ratio is 3:1. So essentially this should be of the salt has the form that is given as x y3. So when it dissociate, so it dissociate to form x plus 3 y minus 1. So if it is 0.01 molar, so it dissociate to give 0.01 mole of x and 0.03 mole of y because of the stoichiometry. So m1 should be, for this case, is 0.01 and valency is +3. m2 is 0.03 and valency is -1. So when we have to find out sigma mi zi square. So it becomes 0.01 into 9 plus 0.03 into 1, and when we get is 0.12. So when we substitute this again in this formula, so what we get is this. Okay, so kappa inverse comes out to be this. So I hope this is clear. So this is very important, how to find out the it is basically called to be a ionic strength. So this ionic strength is the formula for ionic strength is sigma I mi zi square. So that is, we called it to be ionic strength. I am just telling you there is no use of it. Okay, so these are the two questions that we have discussed, and I hope this will help in solving your assignment problems. Okay, thank you.